Good morning, students. Today we will discuss about errors and what are the different types of errors and how to study the stability. So mainly there are two types of error. One is the discretization error. Actually, this is the difference between the exact solution and the corresponding difference equation. And there is another type of error. This is called the round-off error. This is nothing but the difference between the numerical solution and the exact solution of the difference equation. Numerical solutions actually mainly calculated with the help of the computer. So generally, if A stands for the analytical solution, D is the exact solution of the difference equation, and N is the numerical solution from the real computer, then the discretization error is defined as A minus D, and the round-off error it is denoted by epsilon, and it is defined as N minus D. So that is the numerical solution is equal to the solution of the difference equation D plus the round-off error. Now this was our partial differential equation. It is the and its discrete difference equation is this is given by equation number 2 that we have already studied in our earlier section, that is the difference equation, and the numerical solution capital N. What is capital N actually? This is the numerical solution of the difference equation. Numerically, you are solving it by the use of numerical technique. So this N, that is the numerical solution, this must satisfy the difference equation too. So we are using that concept as it satisfies the difference equation 2. So we are getting the equation number 3, where N is the solution of equation 2. So the solution must satisfy the differential equation. Similarly, what is our D? This is the exact solution of the difference equation. So this D, it also must satisfy our equation number 2. So we are getting the equation 4. Now if we difference 4 minus 3, so then we are getting this equation number 5. So now if you look at this case, what does it imply? The round-off error epsilon or the error epsilon, it also satisfies the difference equation too. So from this we can say that the error must satisfy the corresponding difference equation. Okay. So now we come to the another part, stability. Now stability generally it is connected with the error. Now if the errors it shrink or it decreases, or at best it remains same with the change of time. So generally what we denote EI in suffix n. This is the error at time t, and EI n plus 1, this is the error at the next time interval, that is the next time part, that is for n plus 1. So what we have said that if the errors shrink or at best stays same as the solution progresses from the step n to n plus 1, means from the value of time at n to n plus 1, if the errors decreases or at best it remains same, then the solution is known as the stable. And otherwise, that is if the errors grow with the change of time, then it is called as the unstable. And this is the mathematical condition for the stability. Okay, so now what we do, we try to find the error of this particular differential equation or this particular difference equation, that is of equation 1 and 2. Now generally what is the property of error? Suppose we assume that errors either grow or decrease at a particular time interval with the change of x. We have two variables, one is the x and one is the time t. So suppose we assume that the errors it is either grow or decrease at a particular time with the change of x. This is our assumption. So with this behavior, it is assumed that the error must satisfy the Fourier function, or yes. So with that Fourier transform or Fourier series concept, we assume that the error satisfies this equation, or error is of the form where A is the amplification, and Km, this is the wave number. Now what is wave number actually? Let us see. Now this is a sine function, okay, and what is lambda here? This is the wavelength. Yeah, this is the wavelength. Okay, so if your lambda equal to L, you are getting that part, that is sine 2 pi by L. This 2 pi by L, this is called the wave number. So that is in the wave number notation, we have represented this equation in the form of y sine Km x, where Km is equal to 2 pi by lambda, and that is called the wave number. Now what is the physical interpretation? If there is only one sine wave over this particular interval or this particular segment, so and if your lambda equal to L, then your wave number will be 2 pi by L. Okay, this is for one wave on a particular interval. Now if there are two waves, you see this is one wave of wavelength L by 2 and this is another wave of wavelength L by 2. So if there are two sine waves are completely filled within this interval, then lambda will be your L by 2, this is the wavelength. So the value of your Km from this definition will be 2 times 2 pi by L. So that is two waves. Okay. So similarly, if there are m number of waves, sine waves, completely filled up within this particular interval, then our Km will be m times 2 pi by L. So from that we get the idea of what is wave number and what is the interpretation of that m in the suffix. It represents the number of waves on that particular interval. Now we try to find what might be the maximum or minimum values of this m. How many waves? Yeah. So if if there is only a single wave, okay, so then there if there is only a single wave of length L, so that is the maximum wavelength is L, so it corresponds to the m equal to n. So if you look at this part, if your lambda equal to L, there is only one wavelength, so the value of m will be 1 because m represents the number of waves, and if there is a maximum wavelength of length L, means there is only one wave of wavelength L, so your m will be 1. So the minimum value of m must be equal to 1. Now what might be the maximum value? So for that what we do, we divide the entire wavelength into n plus 1 grid points. Okay. Suppose you can imagine that we divide a length by 10 or 11 grid points. So if you divide a line by 11 number of points, then you get 10 number of small intervals between that particular line. Okay, so that we have taken. If there are n plus 1 grid points or points distributed over that particular interval capital L, so what we have obtained, so in that capital L length you are getting capital N number of small intervals. So if you consider one particular increment delta x, what is delta x? This is one part of your small waves. So what will be the value of this delta x? This delta x is nothing but, you see, the increment between I and I minus 1. I is one of your grid point and I minus 1 is the previous one. So your this delta x will be equal to capital L divided by n. Okay. And if you look at this particular wave, so what is the length of this particular wave? This is your 2 times of delta x. So the wave number will be 2 pi divided by wavelength of this small waves. So what is the wavelength of this small waves? 2 lambda delta x. And what is the value of delta x? This is L by n. So what you are getting from this wave number, that there is n by 2 number of waves. So if there is an length of wavelength capital N, and if there is n plus 1 points on this particular length, so this n plus 1 points will give n number of intervals, okay, and the value of each of this interval will be capital L by capital N, where capital L is the length of the whole line and capital N is the number of intervals, okay. So how many waves are there? The number of waves is n by 2. So if there are 2 points, it gives the 1 waves. Okay. So from that particular expression of your equation number 1, this was your beginning equation 1, there is a summation. So this summation ranges from 1 to n by 2. Okay. 1 to n by 2. Now again, if you look at that error, this one, again if you look at this error depends on two variables. One, I related to your x, and n related to your time t. So x is there, function of x is there. So this part, that is the amplification or amplitude, this must be function of time t, okay, because your ultimate error is a function of two variables, x and time t. Further we take that this amplitude, this takes exponential variable. Generally what happens, the error, it either grow or decrease exponentially. It is decreasing exponentially, it is increasing exponentially. So with that factor, we assume that the error is of this form. Okay. And this is the difference equation. So though there is an summation, so what we do, we study for each of this term, for each of this m. So for any m, how we get this expression? What is E n plus 1 represent? It is represents at time t plus delta t. And what is EI at n? It represents at t, n plus 1 will be at t plus delta t. So this is the error. And what is the form of the error? So if you look at the form of the error, it is nothing but e to the power at into e to the power ikmx. So this is for t. Similarly for t plus delta t, what will get? You will replace simply t by t plus delta. So that we are doing. And now some simple calculations, okay, some simple trigonometric identities. And using the condition of the stability. Now, what is the condition of the stability? According to this stability condition, this modulus must be less than equal to 1. So, some simple mathematics, we are getting two cases. Okay. And what is that G? G is defined at this part. So, finally, after some calculation, we have arrived at this is the condition for the stability for our particular these two equations. That is for the partial differential equation and for the difference equation. So I request you to go back with the notes, and or you can follow the computational fluid dynamics by Anderson book, and if you have any query, then please ask.